So today I want to talk about Drinfeld's lemma. So roughly the goal is, so if x and y are varieties over Fp, then what you would like to do is compare the fundamental group of the product with the product of the fundamental groups. And now this fails for at least two reasons. So one is that if I just take x and y to be just a point, then pi 1 of x cross y is still just a point, so it's still z head, whereas the product is two copies of z head. That's just because some of this point Fp just stays Fp and doesn't get any bigger. But so I think that the better question is to do this when you're in an algebraically closed field. So even if we would ask the same question over an algebraic closed field. Okay, over Fp. Still false. So let me explain why this fails in a second. So, or more generally, let me say something about fundamental groups and characteristic P. So say if K is any algebraically closed field on R, and X and Y are say schemes of finite type over K. Then, well, there's a good case. So if the characteristic of K is 0, then it is true. Well, throughout most of my talk, I will just ignore base points, and I apologize for that. So you can put them in when you like. Is really the product. And there's an additional good property there. And actually the two are related. So, and for all x tangents K prime over K, algebraically closed fields, the pi 1 of the base change to K prime is just the pi 1 of x itself. So the pi 1 is really something geometric. It doesn't change if you change the algebraically closed base field. But if the characteristic of K is positive, both properties fail. At least if x is not proper. So let me give an example for that. So if you just look at the simplest example of a non-proper variety, so the affine line, then if you take homomorphism from that into Fp, so Kp is a characteristic, of course. Then this is the same as the état homology of the affine line with Fp coefficients, which by Artin-Schreier theory is the co-kernel of the Artin-Schreier map on polynomials. F maps to F to the P minus F. And so that's some infinite dimensional K vector space. And so if you extend scalars to some bigger algebraically closed field, you're just tensouring up this k vector space to this bigger field, but it changes. You can describe how it changes, but it still changes. This is not invariant.
It's not really a k vector space.
Oh, so well, that's
it's
right.
Big.
That's stupid. Yeah, sorry.
Hey, but it's not invariant.
It's certainly not invariant in a changing k. Yeah. Sorry.
That's p vector space, right?
Yeah, but yeah. Well, I mean, like over k prime, sometimes a similar thing happens, and sometimes you can understand what happens, but well, whatever. And also, I mean, this works for any affine scheme. And characteristic P is this kind of identification. And so from this it's easy to see that if you take the affine plane over this field, it's really not the product.
So I guess you mean the natural map is not an isomorphism, but do you actually know that?
Yeah.
No, I mean, is it known?
Yeah, I don't know, no.
It's not known.
Yeah, I don't know. Sorry. Yeah. So maybe there are homomorphisms in the FP actually are some infinite dimensional P vector space and thus the same and so on. It's probably also that pro P quotients are the same because they have free pro P groups and so on. So, yeah, I don't know. No. So this is a free pro P group with pro P quotient of that, but that's not free pro P, that's a product. So it's probably not the same. Yeah? Anyway, so let me state some lemma which I'm not going to prove, but which says that one can actually deduce this property about products of pi1s once you know this invariance and the change of algebraically closed space field. So say that f, which I think of as a fiber later on, and x be some schemes. I think I can just take any schemes of an algebraically closed field. Okay, and I want that x is connected. And I assume that for all extensions, k prime over k, which are still algebraically closed, f over k prime is connected. And the fundamental group didn't change. Then actually, pi1 of the product is just the product of the pi1s. Sorry, and I want f as QCQX. So later I will state a similar result for diamonds, and then I will give a proof which will actually adapt to the setup as well.
I just can't see the board.
Yes.
Fx scheme over k, x is what?
X is connected.
Connected thing.
Yeah. So I should say then f cross x is connected. And well, I want to talk about fundamental groups, so I better see my stuff's connected. So I should probably have up there as well. Okay, so let me now get to Drinfeld's lemma. So what does it actually say? So we're starting off with, well, let's say any number, any finite number of connected schemes of finite type over Fp. Or over Fq if you like, but it doesn't really make a difference. And so we have, on the product, we consider Fi, which is somehow 1 cross Frobenius, the I spot, plus 1, which is a map of this product. And so as I'm over Fp, there's some no ambiguity of what this Frobenius is. And so what Drinfeld is considering is essentially the quotient, in some sense, of these xi's by these partial Frobeni. And it's not a priori clear what that should be, but you can at least make sense of what its finite état covers should be. So let x1 product up to xn mod partial Frobeni. So these guys are called partial Frobeni, I should have said. Finite état be the set of all y to the product, which are finite état. Plus, so this is supposed to be like if you have something finite état over here, you can pull it back to the product, but then it's supposed to come with a descent datum corresponding to this quotient. And so this descent datum is supposed to be commuting isomorphisms beta I from the pullback under this partial Frobenius to y, such that the product of all of them is just the absolute Frobenius of y itself. The Frobenius of y. Frobenius of x. And this is supposed to be the relative Frobenius. Does that sound right? Yeah. So whenever you have something finite état, the total Frobenius pullback under, like the Frobenius of the whole scheme, the relative Frobenius will be an isomorphism. And yeah. So the point is that if I just have one copy, I don't want to do anything to it. Like I don't want to give an extra Frobenius. And so let's call it theorem, Drinfeld, is that, well, so this forms some from Galois category, if you like. As an SGA1. And whenever you pick a geometric point as a product, you get a fiber functor. So you can define a fundamental group. Again, I'm skipping base points. Sorry, mod partial Frobeni. It's isomorphic to the product of polygons. Good. So this means that if we want to get such a comparison, we just have to X is partially Frobenius. Let's see how this overcomes the previous obstacles. So if x1 and x2 are just spec fp, then that guy, it's our covers, y over spec fp finite eta. So that's somehow parameterized by one copy of Frobenius, plus an additional plus one copy of Frobenius. Which gives another copy of Z hat. So in general, we have n minus 1 extra partial Frobenia, which gives you n minus 1 extra copies of Z hat. So dividing by this partial Frobenia gives you the correct number of base copies of Z. And then we know over there had two partial Frobenia such that the product is something known, and so giving the two of them with this relation is equivalent to giving one of them. So that's good. Okay, and so somehow a version of so the crucial properties, some of them properties that something's invariant under its tangent of algebraically closed fields. So the crucial change algebraically closed space field.
So in Drinfeld's lemma, do we want to assume the xi's are geometrically connected?
No, I think that this guy behaves as if it was connected always.
Okay.
Is it easy to say how you see the previous lemma under this? That if f is such that pi one of all extensions is the same,
Yes.
then how do you deduce this lemma from Drinfeld's lemma?
No, I don't say that Drinfeld's lemma implies this. I say you can directly prove this using.
Sure, but shouldn't it be easy to
So I will, in a second, I will give an argument for Drinfeld's lemma that will somehow use a version of this lemma.
Okay, but vice versa, shouldn't this easily imply that one? I mean, if you knew this is...
Well, Drinfeld's lemma is a totally different
It's
statement,
stronger.
really, right? Because here you're not dividing by partial Frobenia at all.
And that lemma doesn't involve things of finite type over FP.
It doesn't involve things of finite type over FP. So let K over FP be any algebraically closed field. And let X bar denotes a base change to K always. And so this has a relative Frobenius. Fx bar over K, which is xi bar. And so the lemma I'm referring to is that what's always true is that if you take the pi 1 of so x over fp connected variety, this modulo it's relative Frobenius, it's pi1 is equivalent to the pi1 of this thing over Fp. So in other words, the arithmetic fundamental group you had is somehow turned into this, what happens on the Frobenius here. But this works for any algebraically closed field. So concretely, this means that one has an equivalence of categories between y0 over x finite et al. And y over x bar finite et al. Plus an isomorphism between this pullback and y. No, I think like when I want to prove this, I can reduce to the affine case immediately, right? And so let me first say how the lemma implies the theorem. So first of all, this pi1 of x1 cross xn mod partial Frobenius can be reinterpreted by the lemma used for the product as the pi1.
Which might not be connected, right?
Well, this statement still makes sense, and it's true.
Yeah. Oh, you said the lemma doesn't have a connectedness or something.
Let's put this in quotation marks and make this the actual content of the lemma. Of the product over this algebraically closed field of all the xn's modulo all the partial Frobenius. In this lemma, we don't need connectedness. I mean, you can easily reduce to the affine case and maybe even the affine connected case, where this equivalence of finite star covers by descent. And so, yeah. Then now I'm sort of, in using this lemma, I'm getting one extra Frobenius, and it's somehow getting rid of this extra commutation assumption there. And so, pi1, invariant energy change. Algebraic closed space field. Nice product, good. By that kind of argument, you see that thus this spreads out into a product. And so I just want to give an overview of the proof in the scheme case, and then in the diamond case I will make the arguments more precise. By the lemma for the xi's, this then is again the product of the x1. Okay, and so now let me sketch the proof of the lemma. So what we're trying to do here is make some descent from, like if k was fp bar, then this would just essentially be usual descent along the extension from fp to fp bar, except that I'm only giving the action of z and not of z hat, but apart from this minor issue. But here this k could be really big, and still just giving this one equivariance is supposed to descend down to this very small field fp. So that might a priori be quite surprising. So the first step is that this works at least for vector spaces, finite-dimensional k vector spaces. V plus the Frobenius on V, which is an isomorphism between the Frobenius on k pullback of V to V. That's equivalent to finite-dimensional FP vector spaces. Just by base extension. The point is that you can recover the original FP vector space as a Frobenius invariance. So V maps to V naught maps to V and 1 tensor Frobenius. Okay. And conversely, V as a Frobenius maps to. What did I put 2 maps to here? V naught, which is V, the phi V invariance. Of course. By the way, a good reference for this stuff about Drinfeld's lemma is also Galois thesis, which I forget the name of.
The original form of Drinfeld's paper, as soon as you constructible sheaves on.
Yeah, so I guess there's more content in Drinfeld's lemma there, but like I don't want to discuss that. Okay, so okay, so next let's assume that X is projected over Fp. Then you have a similar descent result for coherent sheaves on X. So then coherent sheaves E over the base change to K plus phi E, which is an isomorphism between the Frobenius on K pullback of E and E. Is that what I want to write? Yes, I think so. So those all descend to coherent sheaves. E naught on the guy over Fp. And so here the strategy is to describe everything in terms of rated modules over graded rings by picking an ample line bundle. And those guys in the projective case, they are finite dimensional over K respectively Fp in each degree. And so you can use 1 to descend them. But this seems to work only in the projective case, and indeed this kind of statement fails if it's not projective. Like, you can easily cook up an example for A1. So. So I should have said that we can assume without loss of generality in this kind of, if we want to prove the lemma, that x is affine. And then we can choose a compactification into something projective. X prime is projective. Shouldn't use a bar now. Okay. And so now we can use the following series of equivalences of categories. So if I consider the y over x bar, which I find at tau, plus an isomorphism between the relative Frobenius pullback and itself, then first of all, we can replace this relative Frobenius with the Frobenius on K, because the relative Frobenius for the whole thing is an equivalence. So that's equivalent to y over x bar phi theta plus. So today we will use lots of Frobenii and get very confused about them. As for a finite Ital guy, the absolute Frobenius pullback is canonically isomorphic to y. So that's the Frobenius of y over x bar. Okay, but then if I have any finite Ital cover of this open part of this projective guy, I can just take some normalization inside the whole guy and get something finite normal over it. And this is a canonical procedure, so it still comes equipped with
X is normal?
Fuck. I don't think it's really necessary, but let me assume it's normal. Like, I think you should be able to reduce the normal case anyway. I didn't look this up. Sorry. So that's equivalent to the set of y prime over x prime. Which are finite and normal, plus an isomorphism between the pullback of y prime and y prime. And such that they are tau over the open part. And then, by using the result from 2, this gadget will descend. So we get y naught prime over x prime, finite normal. So normality can be checked after extension to a big field. Plus, such, and also that zeta can be checked there, so such that y naught prime zeta over x. And so these then can again restrict to the open part, and this also determines them. So that's equivalent to y naught over x. Finite zeta. Let's finish the proof.
Why you need normal?
He wants to extend by normalization.
I want to extend my normalization, and so this might change the original guy if it was not normal already, or can I do some kind of relative normalization? mean, how can you describe a vector bundle in terms of finite état covers? So this part for covariant sheaves really only works in the projective case, but in finite état covers are somewhat more rigid. Okay. So that's the scheme story. And so let's now do the diamond story.
So maybe you can use just like cohomological descent. I mean, use like a Tauer normalization.
Yeah, that's what I would try. Yeah.
Yeah.
Take the normalization, then describe everything as finite état covers there, plus some kind of descent datum, which is purely topological in some sense. It should work. Or the SPA DGP version. So all of this is about fundamental groups, so I should first say something about fundamental groups of diamonds. Yeah, so let D be such a guy. Let's say D is connected in its underlying topological spaces. And then a basic proposition is that if you have E over D finite état cover, where D is connected, then all geometric fibers have the same degree, then the degree of E over D is constant. And the point is just that a fixed degree defines an open subfunctor. And there are only finitely many possible degrees, so all of them are connected components, and so like even connected components on the topological space, and so if it's connected, then it must be constant. And so thus, if I have some connected diamond, and X is a geometric point, one can define a profinite group by one D pointed at X such that the usual diagram works. So finite sets with a continuous action of this profinite group are equivalent to E over D finite état, where you have here the fiber over X, which gives you a fiber functor to sets, and you have here the forgetful one. So I guess to get this, I have to verify that finite état covers really form a Galois category in the sense of SGA1. So in particular, that if I have a map of finite état things, then the image is a finite état guy, but locally everything finite état covers are given by finite état covers over the algebras, and so you can reduce all the verifications to the algebraic case.
Geometric points always understood to be like rank 1 things?
Yeah, I better take them rank 1.
Okay.
Okay. Okay. So So we want to replace the varieties xi and Drinfeld's lemma by Spa-D QP. Okay. Actually, I didn't think about what generality, like how general objects you could replace them by. That's a good question, actually. That I should think about. Let's just do the Spa-D QP version. So so first of all, we have to define this kind of thing where we divide by the partial Fubini. So we take this cross Spa-D QP several times. Mod partial Fubini, finite detail covers, to be just the same thing as in Drinfeld's case. So it is finite detail covers of Spa-D QP to the n plus commuting isomorphisms theta I from the pullback under the ice partial Frobenius of E to E. So again, you have partial Frobeni. Because any diamond has a Frobenius, everything being defined on rings of characteristic P. Such that the product is 1 it's the absolute Frobenius of Y, of E. Okay, but here we can make some extra manipulations with this. So, namely, you can also say it's the set of E finite detail over n copies still. But so if I give you the isomorphisms beta 1 through beta n minus 1, which commutes, and you can read off the last one by this equality here. So it's equivalent to give commuting isomorphisms beta I. So I here runs from 1 through n. From E to E. Where now I just runs from 1 through n minus 1. Since I don't have to verify any equation now. But now we can observe that on the underlying topological space of n copies of Spa-D QP, you have the action of f1 to the z times fn minus 1 to the z, and that acts totally discontinuously. It's really and totally discontinuously. So, for example, if ns2, we had this interpretation of Spa-D QP squared as being this perfectoid unit disk, say over QP on CP star, takes a diamond, and then we had the Frobenius acting on that, and there was some scaling on this punctured open unit disk, which was this totally discontinuous action. And so this means that we can actually just divide this gadget here by these partial Frobeni, get a new diamond, and its finite detail covers will just be those guys. So this is isomorphic to Spa-D QP. to the n. Where is this gadget here?
So is it formal that if you have a diamond and an action of a group on that diamond, which acts totally discontinuously on the underlying topological space?
Then you can form the quotient. Yes, that's formal because locally you can like pick an open subset which doesn't meet all its translates onto the group, and this will be an open functor into the quotient, and then you can cover your quotient by such guys. Let's call this now theorem 1. That actually now what we hope to be true is true. So takes body QP to the end. One partial Frobenius, which you can regard as being the fundamental group of this diamond here. That's isomorphic to the fundamental group of QP, which is just the Galois group of QP n times. But again, it's useful to in order to prove this, again, the crucial step will be to show that some fundamental group is invariant in the change of algebraically closed space field. So let's introduce some arbitrary algebraically closed space field into the picture. Let's have a slightly different version. So for this, let's fix K in algebraically closed field of characteristic P. With a discrete topology. So it's not a non-Archimedean guy, so just a discrete guy. And then we have this field L, which is the ring of bit vectors invert P. And so then what should be true is somehow that the Galois group of QP can be regarded as the Galois group of finite tossings over L equipped with some Weyl descent data. And so that's what we will do. So we consider the set of E to n copies of the diamond for L plus commuting isomorphisms beta I between. So we have the relative Frobenius of L over K as at least as diamonds. So that's not the usual Frobenius on L, which comes right from theology from K, but it's some of the other guy, which only exists on diamonds. The I spot upper star E. Isomorphic to E. So let's denote that by spadi L to the n modulo and so then what's also true, and what's not obviously the same statement, is that the pi 1 of this guy, or, well, I will give better notation in a second. Is isomorphic to n copies of the Galois. And so theorem 2 implies theorem 1 by taking k equal to fp bar c. In which case, making this extension to L is introducing one additional Frobenius, but you have one more Frobenius here. So here, I run this again from 1 to
Say that again? So you have n of them down there.
I have n of them down there. I have a priori only n of them as one of them up there, but if I extend scalars to fp bars, so when taking this product, I need to specify one more Frobenius descent. And so, I don't want to spell it out because it's too confusing with all the Frobenia. And now this is a statement which again is trying to compute the pi1 of the self-product of this body L mod 1 copy of Frobenius. So to prove it, will again be, so we will first prove that the pi1 of z guy is invariant under any change of algebraically closed space field, and then we will prove a lemma that this implies that the pi1 of the product is the product of the pi1s. So
we really need to use the part general K. So we really do need the generality of
yes,
general
I do need this generality. And actually, well, let's see this. In a second. Where did I put this? Must be somewhere. Yes, here. So I hope I haven't used the letter X in my discussion in the diamond case so far. And so let me define X to be the adic spectrum of QP modulo its absolute Frobenius. So this now seems to have two copies of Frobenius, but if I extend scalars from fp to k in the sense of functors, so both of these define functors on diamonds, then this will just be the adic spectrum of L modulo the relative Frobenius. Yeah. And so this now again has the correct number of Frobenia too. So that's some kind of real version of Spotty QP. So what you do when you consider Weyl sheaves is that you replace your FP by some algebraically closed field, but instead you require an additional descent datum for the relative Frobenius. Okay. And so what's in fact easy to show is that for any k, the pi1 of this gadget here, meaning finite tile covers over L plus such a descent datum, that's equivalent to the absolute Gara group of QP. Namely, what does it mean concretely? It means that extensions M of L, finite tile, which come with a so one previous step. So if I consider this body L, what's the relative Frobenius? It's finite tile covers. Then again, I can replace this relative Frobenius by the Frobenius on K, because some absolute Frobenius is an isomorphism, so that's equivalent to. Thus, what we have to show is that if you consider M over L a finite extension plus an isomorphism between phi upper star M and N, where phi from L to L is just the usual phi. that this category is equivalent to M naught over QP by base change. But that's essentially this exercise I was giving. Namely, so you can just send M to M0, which is the phi invariance, and conversely, M0 maps to the base extension. And so this is what you have to see is that the phi invariants are big enough. But any finite star extension has a canonical lattice, which is a ring of integers, which is preserved by this Frobenius. And whenever you have some guy with this, where phi leaves the lattice stable, then it will have enough Frobenius invariance. Leaves the lattice OM stable. Okay. So that seemed easy, and actually we need a better statement in our setup. Yeah.
What is that L over K? Maybe we said before.
It's somehow the relative Frobenius in the world of diamonds, right? So I mean, like when you have this usual diagram, K, and it's body, I mean the functor represented by K. Then I get body L here. So there is a Frobenius map, which makes this diagram commute. And so if you take the fiber product here, there you get a unique map here, and that's the relative Frobenius.
Do you have a condition between the beta I stuff?
No, because it's over the algebraic closed field. So there's no total Frobenius anymore a priori.
This is maybe a dumb question, but does SPDK make sense?
Well, it's just a functor represented by K.
Oh, okay. That is, it's not a diamond.
It's not a diamond, yeah.
But SPDL is a diamond.
SPDL is a one. But really, the kind of invariance and a change of algebraically closed base field we need is also for non-Archimedean base fields. And so the key lemma is that for any algebraically closed base field, how can you close non-Archimedean field? C over Fp. So you can form the base change of x to C. And that's still supposed to be just the absolute product of QP. And so this will be equivalent to the fact that the Fogg Fontaine curve is simply connected. Okay. So let me try to get through all the series of equivalences that we need to get there, and unraveling what all these objects are. So So what is XC? Or spiny data covers? It is spadi L modulo the relative Frobenius of L over K times spadi C. And this is a fiber product over K. Sorry. I should have. Sorry. The steps are now unnecessary, given my presentation is in here. So that's just the definition of XC. But then you can again swap some Frobenius here, because some absolute Frobenius will be an isomorphism. So that's
So what is the difference between this and what you did before? That you allow topology for the...
sorry?
So before you were working with an algebraic closed field K.
Yes, but it was discrete.
It was discrete, so you allow a topology now.
Yes, so now it's a non-Archimedean guy, so it has like has interesting topology. And so spadi C will now really be a diamond. So. And so we're now dividing Z factor by
Sorry, this F is which now?
that's some of the absolute, like the F of C. That's what the F of Q. Okay, but that's actually Galois that we know. So let's recall what the p-adic far content curve was. So we were taking the p-adic spectrum of the ring of bit vectors, so this field OC, which was of characteristic P here. We're removing the parts where P and the tangent of P flat are 0, and then quotienting this out, this guy, by the action of Frobenius. Then its associated diamond is just this gadget here. Why is that? So from the discussion of this diamond associated with ZP, we know that if we're doing this kind of thing, we're taking the ring of bit vectors, OC, and then removing the locus where a tangent of a uniformizer is 0. That's some analytic p-adic space, and then we take the associated diamond. And this was the product of spadi ZP and spadi C. And so now we pass to the locus where P is non-zero. Meaning we remove it here, and then in this part we have to go to spadi QP. and then divide by Frobenius, which in both cases was the Frobenius of C. Let's get the result. Okay, and so what's also true is that for any analytic p-adic space, I've used X already, so let's say Y, which say is affine, so spar or R plus. Finite étale R algebras are the same thing as what you get in this abstract way as finite étale covers of the diamond. And so in particular, this implies that finite étale covers of Y are the same thing as finite étale covers of the diamond. So how does this work? So to construct the associated diamond, we were always taking some big pro-Galois cover, such that in the limit it's perfectoid. So some G cover such that R tilde is perfectoid. And then Y diamond was the spar D operator of the tilde of this guy, modulo this profinite group. And so now on an affinoid on a perfectoid space, so giving a finite étale cover of this diamond is one over here with a descent data. So Y diamond finite étale is equivalent to finite étale R tilde flat algebras plus a continuous G descent datum. But for perfectoid algebras, finite étale algebras over tilde are the same as over the original algebra, so that's the same as finite étale R tilde algebras plus a continuous G descent datum. And now by some, so if you want, that's, and then show that this by some pro-finite étale descent, that's the same as finite étale R algebras. So if you want, this category here is again a two limit over such guys over the finite étale covers, because by Gaba Ekik-Ramiro, finite étale algebras over such a completed direct limit are the same as over the usual direct limit and so on. Okay. So thus, the finite étale covers you want to classify, they are isomorphic to finite étale covers of the Fark-Fontaine curve. Of the p-adic Fark-Fontaine curve. And Fark's theorem about the fundamental group of this curve was in the algebraic world, so we still need to verify that finite état covers of this p-adic guy are the same as for the scheme version. Of Fark-Fontaine curve. But both sides can be interpreted as some vector bundle on the space with some extra structures, and vector bundles are equivalent by Gaga, so that's okay by Gaga for the curve. So finally, this is the result for us from the theorem of Fark I mentioned when I was discussing the curve, that finite état covers of the Fark-Fontaine curve, which is some scheme which lives over QP, they all come via the base QP. Fark-Fontaine. Sorry. Good. Thus, we see that this strange X thing there, this QP mod Frobenius, its geometric fundamental group over a base change to any algebraically closed field you could imagine is always a absolute Galois group of QP. And so, so to get what I call theorem 2, one needs the following lemma.
Theorem 2 is the thing with the general algebraic closed field?
And theorem 2 was the guy with the general algebraic closed space field, yes. So let K be some algebraic closed field of characteristic P. And F and X be diamonds over K, such that, so I want X to be connected certainly, and assume that for all C over K, an algebraically closed non-Archimedean field, the base change of F to that guy is still connected, and its pi1 remains unchanged. Then the product F times X is also connected, product over K. And I think I'm using the letter Y for that. And pi1 of Y is a product, pi1 of the, what I will think of as a fiber in a second, and pi1 of X. And so we will use this where x is just the x and f is x is the base change of this x to k, and f is n minus 1 copies of it, and then we argue by induction. Sorry, I forgot one assumption. The fiber is supposed to be quasi-complex and quasi-separated.
Is there a result which would say that if I give you a connected diamond over an algebraically closed field, that it remains connected after any extension of the ground field?
I don't know, that's why I'm assuming this here.
That is for x. You don't.
For x, I don't think I have to care here. Because you can somehow take the base change to this algebraic closed field into this f vector, and then this stays connected. And I think that's I see. Well, let's see. So I'll try to give a proof for this. So first of all, let's try to prove that y is connected. Slightly confused about something anyway. So assume the contrary, so that y is y1 disjoint union y2, with yi are open and closed. So in all geometric fibers, of the map from y to x, which has fibers one of y1 and y2 is empty.
So here we're using this kind of abundance of rank 1 points?
Yes. Yeah, any open and closed decomposition, well, with some sparse CC plus is the same as an open and closed decomposition with sparse COC. And this fiber of yi over a geometric point is bar mapped to x is empty. So it is over a summital neighborhood. U to an x. That's by some quasi-complexity argument. That's using the FC QCQS. And there might be a little bit to check there. That's okay. And so this thus, if I look at the decomposition of x into the pieces where one of y1 and y2 is empty, so I get an open and closed decomposition. Of x according to whether fibers are non-empty. But x is connected. Okay. So the second thing you want to check is that the map from pi1 of the product of f and x to by 1 of x is surjective. So for this we have to show that for all x tilde to x finite et al. And connected, f times x tilde is still connected, but this follows from 1. For x tilde. Okay? So now we can replace x by its pro-finite état cover, pro-finite état universal cover. Which exists in the world of diamonds because the inverse limit along affine transition maps and so on. And so we can assume that by 1 of x is just trivial. Because we can also understand the effect this has on finite état covers over f times x, we just have to give 1 over the universal cover plus the descent data.
X is not assumed to be QCQS?
I don't think I have to assume that, no.
Could you make a descent from this you can cover? Right, the descent from this you can cover.
This here?
No, we're doing this descent, you're saying we descend from this.
Well, the map from the universal cover to itself is somewhat QCQS, and that should be enough, no? Because the inverse limit of finite tau things which are as nice as possible. And so, well, now comes the crucial geometric observation. So, now let's say we have y tilde over y, some finite état cover. And the goal is to construct finite état x tilde to x, which now will be trivial by making this reduction, but anyway, such that in the factorization as follows. So you have this map from y tilde to y here. Here's map to x. And let's call this g and this g tilde. Such that all geometric fibers of g tilde are connected. So this is some kind of Stein factorization for the morphism from y tilde to x. I should thank Laurent Farc for pointing out this approach to proving this to me. So getting such factorization in general is a crucial part in getting, so what we essentially want to get is some kind of fiber sequence for the pi 1. And getting such a factorization is the key geometric input into getting this. And so I'm running out of time. So I guess I have to rush over this. So what happens is that we can build x tilde over each geometric point of x. Just because over each geometric point, it's just find the cover of this f, this geometric fiber of f, and so this we can decompose according to connected components. And what we want to prove is that what happens at a geometric point can be spread into a small neighborhood, such that still all the geometric fibers are connected. So we get some x tilde over x bar. X bar, finite. And finitely many fi tilde over this geometric fiber fc over the points in this x tilde over this guy.
Sorry, C here is the C for the...
C is the for x bar space, yes. We can construct this x tilde. So over this point, we just get a finite set of geometric points. And this factorization means that, well, we have this fiber of y over this point, which is some finite delta cover of fc. And so this decomposes according to connected components. So these guys are still connected. And actually, all the fi tilde come from finite delta covers over the base field by invariance of pi 1. And so then the disjoint union of the fi naught tildes times x over k to f times x is another finite delta cover, which agrees with y tilde at the fiber over x bar. But then, because the fiber is quasi-compact and quasi-separated, and I can choose my neighborhoods of my point to be also of this form, this spreads into a small neighborhood. So this means that in a small neighborhood, we can decompose this finite delta cover as just something which comes from the f factor, and which over the f factor
Sorry, over a
is
small
connected.
étale neighborhood, right? Over an étale neighborhood of this.
Over an étale neighborhood, yes. Or, well. And it's easy to see that it has to be unique, and so then you can glue.
What was the upshot of all this?
What's the upshot of all this? So allow me to give me 1 more minute, and I can take the upshot. So as we assume that pi 1 of x is trivial, x tilde is just a finite disjoint union of copies of x. And so if y tilde is connected, then such a factorization can't happen over something disconnected. So then x tilde is just x. And so thus all geometric fibers are connected. Okay, and so now we have the following composite. We have the pi1 of a geometric fiber of f. It maps to the pi1 of y, which maps again to pi1 of f. We assume that the composite is an isomorphism. On the other hand, that the fibers are connected means group theoretically that this is a surjection. And so everything's an isomorphism. Okay.